Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Wahida Abdul DS700154. Today I would like to presenting our numerical methods project on thermistor temperature estimation. Thermistor are extremely sensitive to temperature, but their circuit produce a nonlinear equation that cannot be solved directly. Our main objective were to apply the bisection and regular falsi methods to find the root, compare their performance, verify our work with MATLAB, and evaluate which is better for a low-cost monitoring system. We started with manual calculation. For the equation f of s equal e to the negative s minus s over the interval 0 to 1. Using the bisection method, we repeatedly halve the interval based on the sign change. The process was steady and reliable. We achieved a root of approximately 0.5671 with the error decreasing consistently at each step. Next, we apply the regular falsi method. Instead of a fixed midpoint, this method draws a straight line between the two interval endpoints and uses the x-intercept as the new root estimate. This gave us the same root, approximately 0.5671. However, the error dropped dramatically, reaching just 0.01514% in only our iteration, which is significantly faster than bisection. Comparing both head-to-head, regular falsi clearly wins on the convergence speed and requires fewer interaction. Bisection, however, is exceptionally reliable because the root is always guaranteed to stay within the strictly bracket. For a low-cost temperature monitoring system where processing power and battery life are limited, regular falsi is much more suitable because faster computation directly reduces energy consumption. We wrote a MATLAB program to double-check our manual work. The bisection output confirmed our finding. It took 10 iterations to reach a root of 0.5669. The relative error steadily dropped from 33% down to just 0.17%, showing its characteristic stable convergence. For regular falsi, MATLAB requires only 5 iterations to converge to 0.5672. The error plunged from 7% to 0.01% almost immediately. This perfectly matched our manual calculation and proved that regular falsi converges much faster for this specific equation. So, what do these results mean? Both methods successfully found the root, roughly 0.567. The key difference is efficiency. Regular falsi gave us a highly accurate answer in half the number of iterations, while bisection is more rigid and foolproof. The computation saving of regular falsi give it a clear advantage in real-time, low-cost applications like portable thermistor sensor. To conclude, we successfully achieved every objective. Regular falsi is faster and more efficient, while bisection offers poor stability. MATLAB verified both approaches, confirming our manual solution. That wraps up our presentation. Thank you.
Hi, my name is Muhammad Afishami bin Muhammad Basri. My metric number is S70305. I want to present about 3.5 about Newton divide difference. For manual calculation, we first apply the third order Newton divide difference method. Since third order interpolation requires 4 data points, we selected the nearest point at 0, 5, 10 and 50 minutes. Next, the first, second and third divided differences were calculated systematically to construct the Newton interpolation polynomial. After obtaining the polynomial, we substitute t equal to 7 minutes into the equation. The estimated humidity obtained was 77.77% or approximately 70.78%. This value is reasonable because it lies between the humidity value at 5 and 10 minutes and follow the increasing trend of the recorded data. Okay, I go to the next section is Lagrange method for the manual calculation. For the second manual approach, we use the third order Lagrange interpolation method. This method constructs basic polynomial L0, L1, L2, L3 directly from the chosen data point. Each basic polynomial will multiplied by its corresponding humidity value, and then all terms will combine to form the interpolation polynomial. Substitute t equal to 7 minutes into This polynomial gave an estimated humidity of 70.78%. Although the calculation procedure is different from Newton method, the result is consistent. This shows that both methods are mathematically equivalent when applied to the same data set. Okay, for the next, the interpolation process was implemented using MATLAB to verify the manual calculation and to provide a graphical representation of the data. The recorded time and humidity value were first defined as data vector in the MATLAB program. Both the Newton divide difference and Lagrange interpolation method were then applied to estimate the humidity value at 7 minutes. The MATLAB code automatically calculated the interpolation polynomial and evaluated it at the specific point. The result obtained from MATLAB show that both interpolation method produce the same estimated humidity value of 70.7776%, which is identical to the value obtained through manual calculation. This agreement confirms the correctness and reliability of the interpolation procedure performed manually. In addition to the numerical result, MATLAB generates a plot to visualize the interpolation process. The original recorded data points were represented by blue scale, while the interpolated polynomial curve was displayed as a smooth red line connecting the data trend. The estimated humidity value at 7 minutes was highlighted using a green square marker, making it easy to identify on the graph. The plot clearly demonstrates how the interpolation curve passed through all known data points and accurately predict the humidity and the required time. Overall, the MATLAB implementation serves as an effective tool for validating the manual calculation and provide a clear visual interpretation of the interpolation result. Okay, for the last part, the comparison table. Finally, summarize all the results obtained from both manual calculation and MATLAB. Manual Newton, manual Lagrange, MATLAB Newton, and MATLAB Lagrange all produce the same estimated humidity value at 7 minutes, which is 70.78%. This consistency confirms the accuracy of the calculation and demonstrates that both interpolation methods are reliable for estimating missing sensor data. The results show the interpolation can effectively recover missing humidity values without affecting the overall monitoring process. While Lagrange interpolation is simple and straightforward for small dataset, Newton method is more efficient when dealing with large dataset or repeated calculation. In conclusion, both methods provide accurate estimate and can help smart greenhouse system maintain stable humidity level, prevent crop damage, and ensure optimal growing condition.
Assalamualaikum and hi. So now I will present about the communication channel elimination. So it is used to determine the unknown channel gains so that signals can be transmitted and received accurately. In this equation, we solve a system of three linear equations using naive Gaussian elimination and the Gauss-Seidel method, then compare the results. First, we solved the system using the naive Gaussian elimination method. We started by converting the three equations into an augmented matrix. Then we performed forward elimination to eliminate the values below each pivot and transform the matrix into an upper triangular matrix. After obtaining the upper triangular matrix, we applied back substitution by solving S3 first, followed by S2, and finally S1. So the final solution obtained was S1 is 1.240, S2 is 0.870, and S3 is 1.170. Next, we solve the same system using the Gauss-Seidel iterative method. Unlike Gaussian elimination, this method estimates the solution through iterations. So we first rearrange each equation so that each unknown variable became the subject. So using the initial guess 0, 0, 0, we updated the values of S1, S2, and S3 repeatedly. After 3 iterations, the solution converts to S1 equals to 1.239, S2 equals to 0.872, and S3 is equals to 1.170.
Besides performing the manual calculations, we also implemented both methods in MATLAB to verify the accuracy of our results. So the program first defined the coefficient matrix A and the constant vector B, representing the system in the form AX equals to B. It then solved the equations using both Gaussian elimination and the Gauss-Seidel method with the initial guess 0, 0, 0 and 3 iterations, and the MATLAB output produced results that were almost identical to our manual calculations, confirming that both methods were implemented correctly. Finally, we compared the results obtained from both methods. The solutions were almost identical, with only a very small difference between them. This shows that the Gauss-Seidel method converts very close to the exact solution obtained using Gaussian elimination. In conclusion, both methods successfully solved the communication channel estimation problem. Gaussian elimination provides the exact solution directly, while the Gauss-Seidel method is more suitable for larger systems because it requires less memory and converts efficiently. Thank you.
In our chapter 6.4 manual calculation, we use trapezoidal rules. Trapezoidal rules is applied with three different number of subtables, namely n equals 1, n equals 2, and equals 4. For each value of n, the interval from 0 to 3 is divided accordingly, and the corresponding function values are calculated using 4 decimal places. The trapezoidal formula is then used to estimate the value of the integral. After obtaining the trapezoidal approximations, Romberg integration is applied using Richardson extrapolation to improve accuracy and reduce numerical error. Next, the percentage true error are also calculated by comparing the trapezoidal rules. The result n equal 4 and the Romberg integration result with the given true value of 3.84x. The accuracy of both methods is compared using the percentage true error. The method with the smaller error is considered more accurate as its results is closer to the true value of the integral. Based on this comparison, Romberg integration is expected to be more accurate because it improves the trapezoidal approximation through extrapolation. In this section, MATLAB was used to verify the numerical integration result for manual calculation and ensure accuracy. The function f equal x equal 1 plus x2 was defined, and the trapezoidal rule was applied using n equal 1, 2, and 4. Romberg integration was then used to improve accuracy through extrapolation. Percentage true error were computed by comparing with the exact value of the integral. Finally, the results were tabulated and compared with manual calculation to confirm correctness and determine the most accurate method. In this slide, it presents the numerical integration results using the trapezoidal rules and Romberg integrations. The trapezoidal rules give approximate value of 3.4539, n equal 1, 3.4949, n equal 2, and 3.4338, n equal 4, showing improved accuracy as the number of subintervals increase. Romberg integration then produced a more accurate result of 3.4070. In terms of errors, the trapezoidal rules n equal 4 has a 0.8221% error, while Romberg integration has a much smaller error of 0.0352%. Overall, Romberg integration is more accurate as it gives the closest value to the true integral. That's all. Thank you.